Okay, in this lecture I will discuss the LD steel making and first of all we discuss the basics of steel making process steps, emulsion formation and stabilization. So, these are the concept covered. First I will discuss the basics of LD, then charging sequence in LD, how the scrap and the hot metal is charged in the LD and in which sequence, and then we will talk about the emulsion formation, that is the major mode of refining in LD, and that is why the LD refining is so fast. I will come to that. And then stabilization and collapse of emulsion, because emulsion is very essential for LD refining. For very fast refining, it is the emulsion that is responsible, and so we have to see how to stabilize it, when does emulsion collapse, and we can stabilize it. Okay. Now, first LD steel making, some basics I will talk about. This is the LD furnace, just we have discussed also during the history of steel making. This look like this. This is almost similar to the Bessemer steel making furnace. In case of the Bessemer, you inject the air from the bottom, and that is not oxygen air. So, and here you can see this is the structure, and then oxygen lens is there. From the top you charge the oxygen over the bath, and what you find it here, this is called a slag gas metal emulsion, and where the surface area, slag metal surface area increases tremendously, and that is why the kinetics of LD is very fast. Okay. Now, this LD process, I say that it is inspired by the Linde-Frankel cheap tonnage production of oxygen, because similar thing, that is the purification of hot metal using oxygen, was also conceived by Bessemer. At that time, Bessemer used air only as a source of oxygen, and it was also autogenous process. There is the oxygen in air react with the impurities, forming energy, heat, and that heat self-sustained the process. And that time Bessemer did not have any access to the cheap tonnage of oxygen, that is why he has to depend on air. But air had major problem that it produces lot of nitrogen into the liquid steel, that is why the steel was not very clean, and problem especially in the cold loading process. So, I will say that is the when the Linde-Frankel process came, that is when it produced the cheap tonnage of oxygen. Immediately after that, that is this LD process came, because people know that if I use oxygen instead of air, then I can alleviate the problem of nitrogen in steel. And also the methodology of charging the gas also changed, that is the oxygen is charged from the top, and it has some meaning because it forms a lot of emulsion where the kinetics become very fast. So, Linde-Frankel process was responsible for LD to take a bath. Okay. And this Linde-Frankel process, you know, it is basically oxygen is produced from air by fractional distillation, but with some process innovation. That is why this process is very cheap. And it was first installed at Linz and Donau. This is the name of the place in Austria, and that is why it is called also the LD process, actually basic oxygen process. This is called the LD, Linz. L stands for Linz and D stands for Donau, and this is two places in Australia, and initially it came with a capacity of 50 ton only. Okay. And oxygen lancing from the top, as you can see, and as I said, this is helps in forming the gas metal slag emulsion, that where the slag metal interfacial area increases tremendously, and that gives the process very fast. And this is an autogenous process. You can see autogenous because you do not have to supply any heat externally, because the impurity oxidation, that is that whatever the generate the heats, that can self-sustain this process. Not only self-sustaining, basically you have to give anyway I will coming to that. There is the 25% solid charge is required as a coolant, because whatever the heat is generated is more than self-sustaining this process. So, this excess heat basically increase the temperature of the liquid steel beyond 1600, and the refractory lining is affected. Okay. For that, to maintain the temperature at 1600 degrees centigrade, we have to add some amount of coolants. At least 25% solid charge is used to maintain the temperature at 1600 degrees centigrade, otherwise temperature shoots up. Okay. because of using oxygen. So, you can know that is the, in case of the Bessemer it was self sustained, but here since you are using the pure oxygen, so its partial pressure of oxygen is high, reaction kinetics is also high, and also because of emulsion formation reaction kinetics is high. So, heat generation is significant, and it is a fast refining as I said, and it takes only 45 minutes, and with emulsion obviously. If the emulsion collapse, then the refining is not that much. The refining process, just like it then becomes a what is that called, open hearth process. In open hearth process, the reaction take place only at the slag metal interface, nominal slag metal interface, and which is very less. That is why it was made little shallower, little wider, but still the open hearth was very less. That is a 6 hour it takes for refining. Here refining hours is only 45 minutes because of emulsion formation, where you can increase the interfacial area significantly. And its capacity today, the LD furnace may be 100 to 300 tons, and most of the plant there is in India, a lot of LD furnace are 150 ton capacity, most of them. 300 tons are there, but very rare. And most of the small scale industry, that is small scale, it does not use 50 ton, right, because it is 100, and small scale industry can use the lower size of furnace. So, this is the basics of LD, and you can see this is the refractory line, highly basic refractory line is there, and I will talk about that thing. And this is the tap hole through which the metal comes out, and this is the lens, this is the mouth through which the lens is injected. Okay. And you can find there is the round corner, basically rounding is there to facilitate the mass transfer into the liquid steel bar. Okay, now I will come to the schematics of the LD process, how the LD process starts, that is the what are the sequence of charging of different raw materials and when the refining take place, all these things. So, first you can see from the scrap box, the scrap is charged directly onto the ladle like this, and then the hot metal is charged over the scrap. So, it has two effect actually, two advantage is that one thing is that if you use the scrap first and then you put the hot metal, then hot metal directly does not hit the refractory valve, because if it does, then it will give rise to some kind of erosion. But if you do that, if you just charge the liquid steel over the scrap, then scrap gives an cushioning effect over the refractory. So, that is one of the that is the reason why it is charged like this. And also there is another reason, that is if you charge the hot metal over the scrap, it also helps in the scrap melting. As we will see, that is the because the inertia of the liquid steel that is poured over it gives some convection, and that helps in scrap melting. How you can see, because the basically scrap melting become heat and mass transfer control, and most of the cases, and that is why if you there is the inertia of the liquid steel, you can utilize to facilitate the heat and mass transfer for the scrap melting. I will talk about that thing. And then in the main flow, after you charge the scrap and the hot metal, and that is this solid charge need not be only the scrap, it can be nowadays DRI or any other kind of steel plant waste coolant people are using. So, you can use any kind of coolant here, not only the scrap, but mostly it is used the scrap and the hot metal. Okay. And after that, this is the lancing period, that is the main blow, and there emulsion forms, and the main reaction, slag metal reaction at a rapid rate take place within very short time, maybe 20 minutes time the refining is over. So, this is because of emulsion formation, and then you take out the sample by this, and then liquid sample, you can see what is the composition and all this thing, and then you can, this is the tapping process. This is called the tapping, when you tap the liquid steel from the ladle to the from the LD to the ladle. This is called a tapping process, and you can see it is there. And if you want to do some alloying, people do the alloy element here, because alloying or deoxidation, if you do want to add the aluminum also, people do aluminum addition for deoxidation is done here. Sometimes alloying also done here, because there is the inertia of the liquid steel you can utilize for mixing or for homogenization of the alloying elements as well as the deoxidizer. Okay, you can do that thing. So, that is why. And finally, it is the slag is taken out in a slag pot. Okay. Now, as I said, that is the thing, that is the liquid inertia from hot metal stream assist in the scrap melting. In this case, when you add the liquid still like this, the scrap melting. If you want to understand the mechanism of the scrap melting, as you know, there is the scrap is liquidus is very high. That is, the scrap liquidus is higher than the hot metal, because scrap contain very low carbon. As a result, its liquidus is high, and hot metal contain lot of iron and lot of carbon. So, its liquidus is usually less. So, usually the scrap liquidus is higher than that of the hot metal temperature. Then how you can melt the scrap? So, to melt the scrap, what is required is that the surface of the scrap has to be carburized by the carbon diffusing from the liquid hot metal to the scrap surface through the concentration boundary layer over the scrap hot metal interface. Okay. So, that is the carburization is required, scrap carburization. If the scrap is carburized, then its melting temperature will decrease, and then the hot metal will be able to melt it, right. So, therefore, the scrap needs to be carburized to lower its melting temperature such that the hot metal can melt it. So, obviously, you can understand, and then the carbon has to diffuse through a, you can see, that is the, if you have a scrap metal interface like this, if you have, suppose let us consider this is the scrap, this is the scrap, okay. This is the scrap, and then there will be a concentration boundary layer. So, your carbon, suppose it is here, it will be like this. This is the concentration boundary layer. Here is the carbon in the bulk, and is the carbon in the, oh right, here it will be just yeah, carbon was less, but carbon has to increase in the surface, right. Carbon is higher basically in the bath, so it is higher, and the scrap it is lower. So, here it is lower. So, from the carbon, right, it is coming like this, correct, it is there. Carbon in the bulk is higher and the carbon in the surface. So, this is the concentration boundary layer. So, carbon is basically diffusing through here. So, this way, this is called the concentration boundary layer. This is called the concentration boundary layer, and if I want to increase the thickness little bit, yeah, right. So, this is the concentration boundary layer. So, carbon has to diffuse through it, and then when the surface, so with time it will increase basically. With time, this profile will go on changing like this with time, and then like this. So, with time the concentration of the surface will increase. As a result, it is also the scrap. So, this side basically is the scrap side, right, and the concentration from hot metal is coming. This is the boundary, this is the CV, and this is the CS concentration at the surface, and carbon is diffusing this way, right. And then you can find with time, this is with time, as you increase the time, the concentration profile will change like this from here to here like that. So, it will go on increasing, and finally, the scrap concentration on the surface will increase, and when that is the way it will carburized, and finally it will melt. So, it is basically the mass transfer right. So, inertia of the liquid stream. Now, if you have the inertia, because inertia will help in this mass transfer for carbon from the hot metal to the scrap surface, it will carburize and it will melt, and then it will melt. So, it is most of the cases the scrap melting. If it is a high carbon scrap, then it will be only heat transfer control. If it is a low carbon scrap, most of the cases low carbon steel scrap, then it is the carbon that is the mass transfer across the concentration boundary layer will be the rate controlling step. So, you have to transfer the carbon, you have to carburize the scrap by mass transfer from the bulk of the liquid hot metal to the surface of the scrap. So, this is essential, and then you can melt it. Okay. Okay. So, this is okay. Now, let us discuss the emulsion formation. What are the steps of emulsion formation? First step is that basically you do this way. With increase in the jet velocity, a distinct cathode is formed. First, this is the oxygen jet is there, it is coming, and if you increase the velocity, then a crater like form. This is depression you can find. There is a slight depression on the hot metal, that is called the crater. A crater forms, and then the liquid droplets, that is the, so peripheral liquid of the crater splash into the slag phase. You have the slag here. So, you have the slag here, and then what happens, and the crater forms, and the peripheral liquid from here, the liquid will be just from the liquid will be splashed into the slag phase, that is the crater. From the crater there is the liquid droplets. So, it tears off, basically it tears off the liquid droplets and throw them into the slag phase. Okay. And as a result, what happens, this slag metal reaction will take place, and because the liquid droplet in the slag phase, and then you have a large surface area, liquid droplet into the slag, and then there will be the slag metal reaction will take place, and mostly it is the decarbonization will take place, because carbon is the major impurity. So, you will form the CO gas there, that is the in situ CO generation will take place, and you can find there will form a slag foam. Slag foam means slag and gas bubbles, that is the CO bubbles, that will form a foam. So, you can find there is the slag foam form, big slag foam forms, which increase the height with progress of refining. As the refining progresses, its height increases, because more and more CO gas is forming, and it is aiding the process of what is that, foam formation, right. So, foam formation is taking place, and then its height will be increasing, and finally forming a slag metal emulsion, and you can find there is the slag metal and gas emulsion formation take place, because it is always, that is the, when the jet is there, and then this oxygen jet is tearing off the liquid droplets and throwing them into the slag phase. Okay. Because you are pumping the energy, and that basically when you tear off the liquid droplets, you are creating the new surfaces. So, so you require the energy for that thing. Okay. So, that is the oxygen jet basically gives that energy to tear off the liquid droplets and throw them into the slag phase, and as the metal droplet goes there, it in situ make the formation of the CO. The CO bubbles forms, it forms an emulsion, it forms a, that is it increases the volume of the whatever foam as well as the emulsion. Emulsion is nothing but there is the your gas, slag and the metal emulsion phase take place, where basically, and in foam means there is the gas and liquid, it makes the foam, and where that second liquid is there, and when the second liquid, like liquid droplet, can independently move through the foam, then it forms a emulsion. So, you have three phase here, one is the gas phase and the slag phase that makes the foam, and then the liquid droplet that is ejected into this foam, they can independently move, and that is called the emulsion. Okay. So, you can say the liquid droplet size may be of the order of 0.4 millimeter, and the surface area increases. You can see the specific surface area, tremendous increase in the specific surface area, 10 to the 5 centimeter square per centimeter cube. So, you can find here there is the gas, slag, metal emulsion. Okay. And here and this is the nominal surface area, this is the slag, you can find this is the metal and this is the slag, and slag metal interfacial area is very less, but here lot of liquid droplets are there, tremendous amount, and as a result you can increase the surface area tremendously, and that basically is responsible for a very high kinetics of the process. Now, see the formation and stability of the emulsion. Now, formation of emulsion requires energy. Why it requires energy? Because when you are making the droplet, you are just tearing the droplet, what you are doing basically, you are creating a new surface. As a result, you have to give energy, surface energy, right. So, that is why formation of emulsion requires energy, and you have an oxygen jet that is continuously pumping the energy for generating this liquid droplet, okay, and throwing them into the slag phase, right. So, formation of emulsion requires energy, and you are getting it from the oxygen lancing. But its destruction is spontaneous. In destruction, emulsion you form, but its destruction, there is collapsing of the emulsion is a spontaneous process. Why it is spontaneous? Because you can see there is in the emulsion you have created a lot of surface area, because all the liquid droplet is there. So, as a result, liquid droplet, gas bubbles are there, and they are with a lot of surface area, because small droplet. So, you have a large surface area in the emulsion, and as a result you have the surface energy is also very high. Depending on the surface tension, you can have a lot of energy in the emulsion. So, emulsion is a very high energy product, okay, and always it will try to collapse and go to the nominal slag metal interface. So, it will always try to, because the state is very high energy state, it will always reduce its energy by moving back to the slag metal system, right, from the emulsion. So, emulsion, that is the destruction of emulsion, is a very spontaneous process because it is a high energy system. Always it will try to reduce its energy to come to the ground state. As a result, destruction is very spontaneous, but formation of emulsion requires energy. Now, see how we can sustain the emulsion. That is very important. You have generated the emulsion because oxygen jet is there, that is pumping energy. You are creating new surface, new droplets, and then you are forming the emulsion. But who will stabilize this emulsion? Because emulsion is a high energy thing, as I said, high energy object. So, it will try to reduce its energy, it will try to collapse, that is spontaneous. But who will stabilize it? What are the factors that can stabilize the emulsion? You have three factors. One is the surface tension. For example, that different interface like slag metal interface, slag gas interface, metal gas interface, all different kinds of interfaces are there. And if you have all this interfacial tension, if the surface tension is high, then the surface energy also will be very high. So, your emulsion will be much less stable. So, your aim will be to reduce the surface tension of all the surface tension. And apparent viscosity, that is also another factor. If the viscosity is high of the system emulsion, that is the slag, that is the major phase is the slag. So, slag phase viscosity is high, then the gas bubbles and the liquid droplet, that is the liquid droplet will move much slowly through the slag to come back to the liquid, that is the main fluid. Okay. So, if viscosity is high, that will restrict the velocity of the liquid droplet towards the, because once this liquid droplet goes, and then again the liquid droplet will try to come down to the parent metal phase because of its gravity, because liquid droplet under gravity will fall and try to join the parent phase. So, if the viscosity of the emulsion is high, then basically the metal droplet velocity, there is a downward velocity will be reduced. So, its residence time will increase. So, that is one way, because the apparent viscosity higher means the residence time of the metal droplet will be higher. Surface tension lower means your total energy of the emulsion will reduce, so its stability will be more. Thirdly, that is the most important thing, is the gas generation by the decarbonization, because when the bath get decarbonized, CO bubbles forms, and that CO bubbles basically stabilize the foam. Continuous supply, because CO bubble will come and then it will escape the atmosphere. So, if you have to supply continuously the CO bubble such that the emulsion always contains significant amount of CO bubble, that will basically stabilize the emulsion by buoyancy. Okay. So, that is important, that is the gas generation by decarbonization can stabilize it. Let us see now what are the surface tension of different interfaces. For example, if we consider the slag metal interface, right. Slag metal interface, if you just compare the values, in the slag metal interface, the surface tension is 800 to 1200 arcs per centimeter square, slag metal interface surface tension. And if you compare this value with only 40 arcs per centimeter square for water mineral oil system. Suppose water is a low temperature analogous for steel, and mineral oil can be the low temperature analogous for the slag. So, it is been found. So, water mineral oil system, it is only 40 arcs per centimeter square, and you can compare how high this value is, 800 to 1200 arcs per centimeter square. Okay. So, most important, it concerns the formation of the formation and destruction of metal emulsion. That is the most important thing, because the metal, because if your surface tension is less, slag metal interface, then you can easily generate the droplets, and again if the surface tension is less, then also the stability of the emulsion will also be higher. So, slag metal interface is very important, and presence of the Fu and SiO2 in the slag has been found to emulsify the iron in the slag. That is the iron, it has been found by experiment that iron emulsify better into the slag if you have significant amount of the FeO and SiO2 in the slag, because they basically help in emulsification of metal in slag. And most importantly, it has been found by experiment that the surface tension decreases significantly during the mass transfer. That is when the impurity transfer from the metal to the slag phase, then the surface tension drops significantly. A experiment has been done here. You can see it has been taken from the book of Felke, edited by Felke. That is the, you can see that is blast furnace BOF steelmaking. It is a collection of several papers, and I have given the reference. What is the experiment is that you can find here, it is the metal you have taken in alumina crucible. You have a metal here, and then this is the slag, okay, and then by taking it up, there is the graphite this thing, that is the, this is basically a float. So if you can take it out, then the slag will come and fall over it, and then you can find this thing. So you have a, you can see initially the metal, that is the interface, this is the slag metal interface, you can see perfectly round, okay. Now when the reaction is taking place, then you can find there is the metal, is the slag, here is the slag, here is the metal. You can understand, this is the metal, this is the metal, and this is the slag, okay. So you can see the slag metal interface has flattened during the mass transfer. That means the surface tension has decreased at the slag metal interface significantly. And then you can see now again the interface is, that is the, again the surface tension is increasing, because as the mass transfer is decreasing, you can see the interface is increasing, there is the contact angle increasing. Here again the contact angle has increased significantly, okay. And finally there is the metal droplet, and when the mass transfer has finished, then metal droplet has regained its old, that is the contact angle again increased to initial state. So during the mass transfer, what you can find, that is the surface tension at the slag metal interface decreases significantly, and that is indicated by a very low contact angle. In this case, you can find almost flat surface. That means your contact angle almost zero, that is the surface tension almost zero. So during the mass transfer, so during the refining process, actually the emulsion can become, slag metal interface become much more stable. That is the most important. The surface tension decreases significantly, so emulsion will remain stable during the refining. So during the refining process, your surface tension, slag metal interfacial surface tension decreases significantly, so emulsion will be quite stable. Flattens at the peak mass transfer. Flattens means basically your surface tension decreases. That is a very good thing. Another thing now you can consider the, so the slag gas interface. You can slag gas interface also interfacial tension not very low. There is a 400 to 600 hours per centimeter square. If you compare this value to 72 hours per centimeter square for the water gas system, so you can see that is also quite high, and it concerns the formation and stability of the foam. And it has also again been found that SiO2 stabilize the emulsion, where P2O5 does not promote the foam formation. P2O5 does not form, while the SiO2 stabilize the foam. That is important. And finally, the foam is primarily sustained by the continuous supply of small size bubbles, because in the foam at steady state you require large amount of bubble, okay, that basically will sustain the foam by buoyancy, okay. So continuous supply, because the gas when it is come, bubbles escape to the atmosphere, so you have to supply the continuously the CO bubble into the phase. So as long as CO bubbles are there, foam is stabilized as well as emulsion is stabilized. When the foam collects, emulsion will also collapse. So that's why in LD refining you have to continue the decarburation to the end of the refining, because if decarburation stop, that is if you finish your carbon, then the emulsion will, no carbon means no CO generation, and the emulsion will collapse. Because you see, whatever you do, surface tension, whatever you decrease and all these things, but finally if you want to stable the, that is the foam, that is the CO2 has to be supplied continuously. This is the most important thing. So in case of the LD refining, carbon has to be preserved to the end of the process, such that decarburation continue to the end and it sustain the foam as well as emulsion. So that is the thing. Only once the supply of CO bubble ceases, foam collapse, emulsion collapse, and refining comes to a halt. carbon should be preserved and decarbonization should continue till the end of refining. This is important. So, another is that metal gas interface. This is also important interface. For pure iron, surface tension is 1800 arcs per meter square. That is the metal gas interface. And the metal gas interface surface tension also can be reduced by using the surface active element. So, if you have surface active element, you can find that in presence of oxygen and sulfur, how the surface tension decreases from 1800 to it can come to 1200. Okay. So, with oxygen also from 1800 to it come to around 1300 at atomic percent of 0.1 weight percent. Okay. So, you can significantly decrease, but still the value is high, 1000 and 1000 arcs per centimeter square, 1200, 1800 to 600 arcs per centimeter square you can reduce, but that is not very significant, but still this is the surface active element reduce this surface tension, because when the surface tension decreases, obviously the stability of the foam increases, and that is a good thing. So, during refining also surface tension in the slag metal interface decreases, again surface active element reduces the surface tension of the metal gas interface. All these are welcome thing, because you have oxygen sulfur both into the bath. So, these are helpful basically for reducing the surface tension, for stabilizing the emulsion, and decreases significantly in presence of surface active element like oxygen and sulfur. So, the reference is Ghosh Chatterjee and the Felke, as I said, blast furnace steel making volume 2, process technology division. There is the Iron and Steel Society of American Institute of Mining, Metallurgy and Petroleum, USA 1975. So, Felke, this book is edited by Felke and is a very good book for BF steel making, especially for the emulsion. So, in conclusion, we can say there is the first kinetics in the LD furnace is due to formation of emulsion that increases the slag metal interfaciality by manifold, right? And the oxygen jet help in formation of the emulsion, and the stabilization is influenced by the surface tension, continuous supply of CO gas bubble. That is very important. So, oxygen jet creates the emulsion, basically they tears up the metal droplet and throw them into the slag and they creates the emulsion, but stabilizing the emulsion, most important thing is that your surface tension at different interface, slag metal interface, metal gas interface, slag gas interface, and all these things we have discussed. That is in case of the slag metal interface, the surface tension decreases significantly during refining, that is the welcome thing. And another thing is that if you have SiO2 FeO, that also help in emulsifying the metal in slag. And in case of the foam, it is the continuous supply of the CO bubbles that is important. Although the SiO2 in the slag stabilizes the emulsion, but if you want to have a very stable emulsion all the time, you should have a continuous supply of the CO gas bubbles. That is very important. And surface tension at the slag metal interface, that I say it can be reduced, that is the thing. And that is most important. That is why, since it is the CO gas bubble that will stabilize the emulsion, there is the foam and the emulsion. So, it is very much essential, you must preserve the carbon to the end of refining. That is called the catch carbon technique. By somehow you have to do, and people do it by blowing practice, I will talk about that. You have to have a proper blowing practice such that you can most efficiently and most economically you can control the decarbonization such that the carbon remains to the end, and you can refine into the emulsion as long as the emulsion is stable, right. Okay, so that is the thing in this lecture. Okay, thank you very much.